class, welcome to the next section in the last chapter. So this is 13.4, the comparison test. So comparison tests are fairly easy to understand, although they can be hard to come up with. So basically what we're doing in this section is we're taking the series that we want to determine convergence on, and we're going to compare it a to another series that we know converges or diverges. Okay, so very similar to kind of what we do with the squeeze theorem, where we're trying to bound something either above or below, and then depending on what the series that we're bounding it with does, will let us know what the series itself that we're interested in does, whether it converges or diverges. Okay. So let's go ahead and kind of flesh out the formalities. So for the comparison test, suppose that we have two series. We'll call one series A and series B. Series A has terms A sub n. The second series has B sub n. Let's say that both of these series have all positive terms. Okay. If the second series, so we're going to say that the first series, A sub n, is the series that we're given and that we want to determine convergence of. So let's say if the second series, the one that we are comparing the two against, or the first one against, let's say that that second series is convergent and that term by term, every value in the first series is less than or equal to the value of the appropriate term in the second series, then um, the first series is also convergent. So basically what we're saying is that if this is always smaller in value than a convergent series, then the first series has to converge as well. Okay. Part two of the comparison test is the complete opposite of that. So let's say that B of n, B sub n is divergent. If A sub n, term by term, is always larger than a divergent series, then the first series, the one that we're interested in, also diverges. Okay. So makes sense there. So let's look at some examples. So we want to discuss the convergence of the following series. So for the first series, we're going to have 1 over n to the 3 halves minus 1 half. Okay. Now it looks very, very similar to a p series, right? I would like to compare this to 1 over n to the 3 halves. I know 1 over n to the 3 halves without this negative 1 half being attached to it is a convergent p-series with a p-value larger than 1. Okay. I wouldn't necessarily use the integral test here because this integral can be kind of difficult because of this 1 half here, right? When we try to do u substitution, it should still work. Although the integral itself might converge, diverge, and we might not be able to actually make a, uh, discuss the convergence of this based on what the integral does. We'd have to test it out. Um, I want to manipulate this thing so that I can then compare it to the P series. So I have to be kind of fancy when I do this sometimes. The thing that I'm looking at, okay, that I want to compare it to is a convergent P series. So what I need then is I need this series to be less than or equal to term by term to the series that I'm going to compare it to. So it looks like a convergent p-series. I want to work out some inequality here so that this is always less than or equal to the some function that I'm going to come up with that I know converges. So the first option would be to just always subtract this 1 half, right? Let's say I always subtracted 1 half. Would, if I subtracted this off, if I had just 1 over n to the 3 halves, would this always be less than or equal to that that second series? I don't know. Let's look at it, right? So here, if I compare this to just 1 over n to the 3 halves, this looks like the denominator would always be smaller, right? And if this denominator is always smaller, then that means that this whole thing is always larger. So it would actually be larger than if I just took the straight up 1 over n to the 3 halves p series, right? Because remember, a smaller value on bottom means a larger value in total. So if I had a larger value here, I'm not actually always less than the thing that I'm trying to compare to. So if my series that I'm given is larger in value to something that converges, there's no guarantee that it converges also. Okay, so that wouldn't be a good comparison. So let's kind of manipulate this a little bit first and see if we can get this into a nicer form. So let's do some equalities before we start bringing in inequalities. Okay, inequalities are nice because I can just kind of start chopping stuff off. So let's kind of first try to get rid of this fraction if I can. So let's change the form of this so that I multiply, let's say, top and bottom by 2. If I do that, this turns into 2. This turns into 2, and this turns into -1. Okay, so now it's an equivalent form because I multiplied the numerator and denominator by the same value. So I multiplied it times 1, so I didn't change the value. But now I might be able to do a better job of comparing this to something, right? So if I compare this to 2 over n to the 3 halves, this now is always smaller than this value, okay? Because I have um, a larger value in the denominator here than I do here because I'm always doubling this value and the subtracting one. So if I'm always doubling this value, that means that I now have a smaller value on this side than here, right? Like if we compare the denominators, 2 times something minus 1 is always larger than the thing itself, right? So this is going to be smaller in value because it has larger denominators. So now I have bounded this term by term by a series that I know converges, right? If I pull this 2 to the outside, it is 1 over n to the 3 halves times 2, which doesn't change the value of the, well, it changes the value that it converges to, but it doesn't change the convergence. So this is a convergent p series with a p of 3 over 2 or 1.5, which is larger than 1. So I know that my series is always less than or equal to a series that converges. So this has to converge as well. Okay, so that's an example of the comparison test. So we'll do a couple more, and that's basically it, right? So the test is not hard, is you just have to be creative sometimes. And if you start to manipulate something and it's not kind of going your way, go back and start over again, right? So sometimes you have to try these a couple of times. Also, try to understand what you're doing, right? If I know that this already looks like a P series, how can I manipulate this so that I am always less in value, right? If what I'm looking at is converging, I need term for term this to be less than the thing that converges. If this looks like something that diverges, I want to compare it with something that's less than it that diverges, right? So these two conditions of the comparison test are gonna what is what drives me for sort of how I'm trying to manipulate this series that's given to me. Okay. Okay, so for the next series, we have the sum from n equals 1 to infinity of 1 over natural log n plus n. And so if we look at this, we have to be kind of creative, right? So natural log of n plus n, is there anything that I can maybe simplify or compare this to for natural log of n, and then how does that compare? Well, natural log of n, if I think about it, is always less than just n itself, right? So if I compare this to just n, I would have 2n, right? And so I would then have something larger term by term, right? Because my smaller, I'm sorry. I would then have this thing being smaller than something else. And so if the denominator is smaller, I would try to be looking for something that it converges to. But if I compare this to 1 over n plus n, well, that's something that I know diverges, right? So that's a p series with n equals 1. So let's see what we do here. So again, this is always larger than just 1 over 2n, right? Because if I 2n being larger than, so n being larger than natural log of n, so the denominator here is larger, so this is smaller, right? So this I know diverges, and this is now larger than a divergent series, okay? So since this is larger term by term than a divergent series, this has to diverge. Okay. So the limit comparison test, right? Suppose that we have two sums, A and B again, that are series with positive terms. If the limit as n goes to infinity of the ratio of n over b is equal to a constant value, where c is a finite number. So again, here I'm looking at just the sequence term, the formula for the sequences, and C is a positive finite number, then either both of these series converge or both of them diverge. So again, what I would be doing here is I would be comparing my sequence or my series AN with another series, and I would just take the limit as n goes to infinity and look at what happens for that formula for their sequences, for the sequence of terms. Okay. And so that divergence or convergence could be determined by that limit value, right? So let's use the limit comparison test on the previous examples that we just had. Okay, so this will kind of verify whether or not we did this right by comparing it to looking at the series that we compared our given series to. So for the first one, we had 1 over n to the 3 halves minus 1 half. So we compared it to 2 over n to the 3 halves. So we'll just take the first sequence, okay, the first formula for the sequence of terms over the second. I'm going to take n to infinity, so obviously I want to simplify this first, okay? So when I do that, um, I get n to the 3 halves over 2n to the 3 halves minus 1. You might need to do that on paper for yourself, although we did have the work already, so you really are just kind of verifying this, right? Um, and so here, the ratio of this is the same, right? N to the 3 halves grows just as fast as this n to the 3 halves. So we're just looking at the ratio of their leading coefficients, which is 1 half, which is a finite value that is larger than 0, 1 half, which is larger than 0, which means by this limit comparison test that they both converge because we know that n to the 3 half power is a convergent p series, right? So therefore, this is convergent, which is exactly what we got before, right? So since this sequence, the series that we compared it to is convergent, by the limit comparison test, our given series is convergent as well. Okay. So doing the second one, we had 1 over natural log of n plus n. So we take the limit, the first series on top, that second series that we compared it to on bottom. So this is a nice way for us to check our work as well. If we did the comparison test and we're not very sure of our answer, we can just check it with the limit comparison test. So taking these limits, we know natural log goes into infinity. This goes into infinity. So let's flip this and multiply. So we're going to get 2n over natural log of n plus n. Okay. And so the limit here, um, I don't really I guess the 2n and the n are the leading terms, right? This n grows larger than natural log of n. So the ratio here is going to be 2 over 1, so 2, which is a constant value that's greater than 0. And so since we know that 1 over 2n is divergent, that means that they are both divergent, okay, as per the limit comparison test. And that's our example, okay? So that verifies that comparison that we did previously, right? So let's determine whether the series converges or diverges for the following example. So again, we're just kind of doing a few examples here so you can see how you can come up with things to compare, or whether just using the limit comparison test is better. So here I have n plus 1 over n square root n. So if we think of a way to try to compare this, well, guess what? N square root n is n to the 3 half power. So we're kind of very similar to what we're doing before. Okay. So if I look at what this is, just looking at kind of a comparison in general, this is pretty much n on top, n over n to the 3 halves. If you cancel those out, that's what, n to the 1 half, which is a divergent P series. So if I compare this, that's just me verbally doing it without putting it on paper. So um, here, this n root n is the same as n 3 halves. So really what's driving this is this n on top and this n on the bottom. The plus 1 just kind of comes along, but we can ignore it in the grand scheme of things when we're comparing things. So if I kind of just look at these two n's, right? So first and foremost, if I subtract this 1, this is always larger, okay? And if I simplify this, again, I get 1 over n to the 1 half. So this is divergent. This series is always larger than this divergent series, so this has to diverge as well. Okay, so this is a p series with 1/2, which is less than 1. So our series, as compared to a divergent series, is larger always, so it's divergent also. Right, and so for B, we have natural log k over k. So again, the easiest thing to compare natural log to is just k. So if I compare this to something, I would compare it to k over k. This will always be less than k over k, right? And k over k is just the sum of ones, but that diverges, right? So it's always larger than just 1 over k, um, which is a divergent series. So I was going to go k over k, but I want something smaller, something larger than a divergent series. So if this diverges and this is always larger, it's gonna diverge as well, right? So for every k larger than 3, this is true. And remember, our divergence and convergence is really determined by the tails, right? What's happening in the long run, not really what's happening at the beginning of the series. So this is the harmonic series, which is divergent, right? We know 1 over k diverges, so this is bigger than a divergent series, so our original series is also divergent. Okay. The series of 1 over n to the n. Okay, so this is a little bit different. So let's see how we can try to compare this, right? So if I take 1 over n to the n, this is always going to be less than or equal to 1 over n squared because these are very large values on the denominator. So overall, this whole thing is rather small. So 1 over n squared is going to be larger, right? So for n equals 1, this is just 1, and this is 1. For n equals 2, this is already smaller than n squared, right? Because this will just be 1 over 4, and then, yeah, this will be 1 over 4 as well. And then I'll have 3 cubed, which is in fact less than if I had just 3 squared. So I know that this converges. It's a p-series, and so this is always smaller than a convergent series, so it converges as well. Okay. So I compared it to a convergent p-series, so it is also convergent, right? And I believe this is our last one. Here we have e to the 1n power over 1n. So I'd like to try to compare this to something, um, maybe to e to the n over n, okay? And if I can't find anything, then I can just go ahead and do the limit comparison test, right? So here we're going to compare it to the harmonic series. This is nice because that'll help me get rid of this n in the denominator. So when I flip and multiply this, I will have just e to the 1 over n. Okay. As this goes into infinity, this goes to 0. E to the 0 is 1. So the limit of this is 1, which is larger than 0. So since I compared it to a divergent series, it diverges as well since I came out with a positive constant value. Okay. So since this is the harmonic series which diverges, this series that I am comparing it to is also divergent. Okay, so a very short section. I think like the next 4 videos are rather short, to be honest with you, very similar length. Um, so we're really just gonna run through some tests, and then towards the last 2 sections, we're gonna or the last 3 sections, we're gonna really sit down and talk about series. Pretty in depth. They'll be rather long sections, so you'll have some short videos coming up, and then the last, I want to say 3, maybe 4 are not so short. So I hope you guys are enjoying the course, and I will see you on the next video. Thank you.